Okay, so here we start with where we were before. So the first question I want to ask is that if the last lecture is as a definition of this matrix is clear or not. So if I recall so that we gave two definitions of this matrix. One is this thing. S beta alpha is, maybe I should rewrite it in a clean way. So what we did was defined as beta alpha is psi beta minus psi alpha plus, right? So it means that you start with some kind of state that looks like phi alpha at late time, as very early time, and then you see what's the probability that at late time it looks like phi beta. So that's essentially the point, the amplitude change appearance. It's important that there is actually no actually any kind of time evolution implied here, but what basically it is phi beta, then v infinity minus infinity phi alpha, right? This is what we are trying to prove. Okay, that is what we are going to do today. So, but this as a definition, is this clear? So that is something, so this is what I want to ask, is this definition clear? Now, where it appeared last time was that what we wanted to do is to look at the time evolution of psi alpha plus at very early time. And we got this thing that at late time, so I'm not putting, it's understood as a vector, of course, it's as a ket vector. This is equal to, one second, I written it already somewhere on top. Is this right? So we start with something like a group wave packet, which is a superposition of psi beta plus from at early, and then we try to evolve it in future. And just give me a second, okay? Okay, so this is psi alpha beta is this amplitude that we have got, and then it okay, let me try to, okay, so so this is what we derived last time. When you take a group wave packet, then at very late time you get a behavior of this kind. So as t goes to infinity, so only at t goes to infinity you have a energy momentum conservation, and also momentum conservation is also always there because of the interactions conserve momentum. Then you have this particular thing, and what I've done here is simply to insert a complete basis of states, because at very late time, when I take its one second, please. Okay, so here at very late time, what is happening is that you start with some wave packet, and at late time, the out state would also be a free wave packet, right? So therefore we can simply so what you do is that you simply put a complete set of basis states here, and we can write you can take this expression and also this is also an exact expression, right? Because we know that the eigenstates, that it's also an H eigenstate, that is how it will evolve with time. And then what, okay, let me kind of go through it again. So what we did was, there are two ways to go it. Maybe I should clear up some stuff here. I'm sorry. Okay, so what we have done here we assume that, so we use the fact that H psi beta plus is equal to E alpha E beta psi beta plus, right? So we started with an in state and evolved it in time. And then we took this inner product and used the fact that D alpha psi alpha minus is equal to identity. It's a complete basis of states. We inserted it here. And therefore, if you take a in wave packet, at late time, it will look like this, right? It will look like this expression. And this is where S alpha beta comes in. And there's yet another computation that we did using the Lippmann-Schwinger equation here, and we got this answer, right? If we evolve a wave packet in the future, if you go through the lectures, you see that you get this expression. So now if you compare this and this, right, we simply get that S alpha beta has to be this. Okay, so I hope this is clear. So S alpha beta is going to govern how these things are. So basically, it's a transition amplitude. That's the proof. Okay, and it comes from the fact that there is a one-to-one correspondence between in states and out states, which has the same energy.
Sir,
yeah,
I have a question in that where you found that residue e power delta e t by h bar. Could you go to that part?
Just give me a moment.
Yeah,
okay,
sure.
I should be very careful here that both of these expressions are true at t goes to infinity. Okay, so this is a wave packet as a, okay, so this is only true at t goes to infinity, and of course, and here also it is true at as t goes to infinity, because otherwise you do not get this delta e alpha minus e beta factor, right? So okay, anyway, okay, yes, Kabir, what you were asking?
That pole we found out, e power delta e t over h bar.
You are talking about this pole?
Maybe a little above, where you wrote that uncertainty relation on, like the t must be, yeah, here. Sir, down, where you wrote t is much less than, yeah, but like, sir, but here t should be,
no, sorry, what it should be greater
yeah,
sorry for that. Yeah, no, it was a typo. I'm sorry. It means what it should have been greater. For large times, it will be energy. This effect of these poles would simply decay. Yeah. If you're at finite time, certainly not. At large time, it will decay. So here, here it is. If you are closing the contour in the upper half plane, this should decay for t goes to, yeah, at because so you take either plus or minus, right? So here you take the +1, and so here I'm basically trying to close the pole in the upper half plane. Yeah, and t is and here t is less than 0. Similarly, you have to do it in the other lower half plane for the when you look t goes to plus infinity, and so as for any t greater than, if t is large compared to this, the contribution of the pole is very tiny, exponentially small. Yeah.
Sir, and like H and H naught have the same spectrum, or is that
no? Again, H and H naught has not the same spectrum. That's not true. But if you are, but when we are evolving, the point is that, as I said again, let me try to repeat that again.
But like, there's always a corresponding.
There is a corresponding thing which at very early time and late time, the wave packets evolve in a similar way.
Correct.
And
but
it only makes sense.
Also same, right?
Yeah, the energies are also the same.
Then they must be having the same spectrum, right?
No.
Or are you saying
again,
one of them is a subset of the other spectrum, or what?
No. So here the statement is as follows, that the way to understand in states and out states are that as t goes to minus infinity, as t goes to plus infinity, the wave packets have same evolution. So basically they have the same spectrum. There's a one-to-one correspondence.
So they have
the way
to
think of, okay, again, so the way to think about it is go back to the quantum mechanics case that you have this bump, right? It's not true that that the free Hamiltonian and with that finite bump, they have the same spectrum. But if you evolve the wave packet, so if there's a bound state, then it simply stays there. It doesn't evolve to t goes to plus infinity or t goes to minus infinity. So the wave packets, then it means that there is a corresponding state, because at very early time and very late time, when you are far away from the bump, the energy should be precisely the free energy.
Okay, but
That's what it means.
but there's no reason for us to believe that psi, which is the pre-evolved this free state, that energy E alpha should be the energy of the eigenstate psi alpha. But
So
that is
I
the
don't
case.
think you
That's
should.
what we assume.
I don't think you should
Is
think
that
in
what
the
we
way
assume?
that it is. It is not an assumption. It is sort of a, yeah, sort of. It is a.
So so if you open that, like I did go through Weinberg again, and like I just went through it, and in that he mentions that we assume that the spectrum of H and H naught is the same, or
Well, what he
similar
means by
statement like
assume
that.
is
What
as
he
for,
means
no,
by that is,
what he means by that is that he commits to a definition of H naught, which is something that it means that you're using the physical masses, because the interactions can also change the mass of the theory, mass of the free particles.
okay.
So that there is some subtlety that we will see, that, but that's the subtlety that comes in when you have this many body theory or many particle theory. So the masses of individual particles can be renormalized by the interactions. So the properties of the, so basically you are trying to, so what he's basically talking of the physical masses. So H naught captures the actual physical masses that you measure. And so it's a little bit subtle, but for the moment, we don't need to go into those kind of subtleties. It's simply that when you are at very early time, you should, because of the way you're designing the experiment, the particles are not interacting with each other and they're effectively propagating freely. Like in the quantum mechanics example, when you are very far away from the bump, it is. So I don't think it is important to think about it as an eigenstate. I think the correct way to think about it is as follows: that it is it's sort of the wave packet moves as if it is free.
Okay.
I think that's the best way to put it.
Sure.
I know it looks very confusing when you put it in the time independent language, but basically the I epsilon, the I epsilon prescription. Wait, let me finish. So the I epsilon prescription is what takes care of it. That in what sense you are making this statement, right? I mean, so actually this is quite a subtle equation, and this is why I took 2 lectures to go over it, and even now I'm spending more time on it, because I completely agree this is not it's not a very easy thing to digest. This equation. This is the Lippmann. It looks simple, but it's not that simple. It's essentially this I epsilon plus or minus I epsilon prescriptions have all the subtlety hidden, which is there is no time here, but one should understand it as sort of a Fourier as a Fourier transform of a theta function. That's the main thing that I'm going to show now. So Kabir, anything else?
No, sir. Yeah, nothing.
Yeah. So what I'm going to say is that indeed the interactions could imply that you have some different kind of eigenstates which are not in one-to-one correspondence with the free Hamiltonian. For example, suppose you start with a gauge theory where you have some electrons or electron-like thing called quarks and gauge bosons and things like that. So you could have states in the theory which are like monopoles, which are magnetic charges. So these are like field configurations that are finite. They're like lumps of field configurations that have finite energy. And when you quantize the full theory, you can show that they behave like particles. But the point is that the energy of these particles go like e to the power minus 1 over g often. Is with the coupling, it has no analytic expression. So one of the important things of this kind of states that we are talking about, in state and out state, they have a very good analytic. So when you turn the g goes to 0 smoothly, it goes to there are one-to-one correspondence between the states of the and the energies also of these kind of states but if you take g goes to 0 limit in e to the power minus 1 over g, they simply disappear, which means that without the presence of interaction, these kind of states, these kind of configurations cannot exist in the first place. So there are, of course, these kind of objects, and I will come back to them. So it turns out that if you remove this kind of objects, also you will be able to get perturbatively, which is a unitary S matrix, just between this class of in states and out states, right? It should be possible. That is simply because if you take an analytic function, if you have two different parts of it, one that's analytic and the other that's non-analytic, the analytic part on its own should be unitary. So yeah, that is roughly the reason why this works this way. So in experiments, you are not able to. Well, what we usually do is to look into only this class of states, right? This is what we do, and because these are the experiments that we can actually physically do. That doesn't mean that monopoles don't exist or this kind of bound. I mean, most like the reason we don't find them in nature is because this kind of monopoles configurations. Yeah, you could ask questions. Why don't we find these kind of weird things in nature that are not like in this kind of in-state out states? The answer has to do with inflation of the universe. So these kind of states, because they're very heavy, they could have been produced only in the very early universe. And because of inflation, they have so much diluted away that we don't find them. But one of the predictions of gauge theories is that you should find such monopoles. They should exist. And in condensed matter physics, people have been able to find these monopole configurations as predicted by quantum field theory. Okay. All right, so let us try to go ahead. I think, I hope you will understand this matrix properly, what it means if you don't have. So this is what we are going to prove today, that this matrix is nothing but this V operator, which is U tilde U dagger. If you remember, U tilde is evolution with the full H, and this is evolution with H naught. And this is what we are going to show now. Okay, so let us start that today, but to start it, we should start with this three things that I mentioned last time. So one thing is simply this, that if I take this integration, I should get minus 2 pi I theta t. This is something that I showed last time in the last 5 minutes. Should I go over it again? Anybody? So please don't be hesitant. Let me know if I have to go over it again. I will go over it. Okay, so since there is no request, I assume that it should be clear. Just watch the last part of the lecture, last lecture. And the inverse Fourier transform is defined like this. So you see that when I'm defining a Fourier, sorry, when I'm defining a Fourier transform, I'm always using e to the power minus e omega t, right? Now we cannot. So can somebody tell me why I'm stuck to this convention? Why cannot I use e to the power I omega t to define the Fourier transform? I could have done that. It has to do with time evolution. The way we do time evolution in sorry, yes.
No, sir, please go.
Kabir? Yeah, you were trying to give the answer.
No, sir, like you just said it, time evolution is e power minus IHT or something. So
yeah, so the way you do it is if you try to evolve a state, what you do is that you take d alpha e to the power minus e alpha t. So psi is equal to d alpha g alpha e alpha, right? So you see that it is sort of a Fourier transform of a state. It's a Fourier transform of psi in a way. And e to the power minus e alpha t by h bar is what we are using to do time evolution. And so e alpha by h bar is omega, the frequency. So you see that we have to do it in a consistent way because if we are using, once we're saying that we're using time evolution operator in this way, it means that is you're committing to a certain definition of Fourier transform. And similarly, when you do the, if you remember, so if there's similar comment on the momentum. For the momentum, it should be the other way, to the power ip dot x, not the, or k dot kx, not I, because that's the way we define it. So once you make a certain commitment, you have to also stick to the commitment in a consistent way. So if this is a Fourier transform, the inverse Fourier transform is this. Note there is no factor of 2 pi. usually, sometimes people do this, they put a symmetric factor of square root 2 pi in both cases. But here I don't do that. I put a factor of 2 pi. Okay, what you can put a factor of 2 pi here, and then you get minus I theta t. And in the inverse case, you don't have a factor of 2 pi then, right? Because for the following reason that, yeah, 2 pi h bar is this. So let us see if it is consistent or not. So first, let us try to do one thing today, which is useful. So to see some consistency. So if I write 1 over omega plus I epsilon, this object is, if I rewrite it explicitly, it becomes omega by omega square plus epsilon square plus, sorry, minus I epsilon by omega square plus epsilon square. Okay. So let us look at this function first. So this function, if you plot it, it looks like this. If I plot, let me call this function as principal value of 1 over omega, principal value epsilon. So if I plot this as a function of omega, so at very large omega, it behaves like 1 over omega, of course. So it should decay like 1 over omega here, 1 over omega. But near omega is equal to 0, it is like behaves like this, right? So this is a plot of this function as a function of omega. So what is this doing is that it's cutting out. So there is a 1 over omega singularity if there was no epsilon, and you are cutting out a small region of epsilon from the origin, right? This is what it is doing. So essentially, it means analogously some kind of contour prescription. So you should think of it as a distribution. A distribution is something, it's not a function itself, but when you integrate with another function, it makes sense. That's the way you should think about a distribution. So it becomes like this. So if you integrate p1 over omega with some function of omega, it means that you are basically cutting out a small region first, and then taking the limit epsilon goes to 0. Okay, so that's what it means. So it means that you are taking out a small region around the origin, and then taking the limit epsilon goes to 0 slowly. Yeah, that's what you mean by the principal value or principal value integral, or principal or Cauchy principal value. It's often called Cauchy principal. Sorry. So now what is this object, epsilon by omega square plus epsilon? How does this look, right? So if you're very away from the origin, it decays like 1 over omega square. And it looks like a sharply peaked function, right? And the peak is at omega is equal to 0. This is how it looks, epsilon by omega square plus epsilon as a function of epsilon. The tail is 1 over omega square. So the interesting thing is as follows. Let us integrate this object d omega epsilon by omega square plus epsilon square from minus infinity to infinity, what we get. So if you change variables, omega goes to omega by epsilon, right? So what happens is, let me think. Yeah, omega by epsilon. Yeah, if I change my variables, then this becomes equal to say x. This becomes dx and 1 over x squared plus 1 from minus infinity to infinity, which is nothing but pi, right? Because I divide by epsilon here, multiply by epsilon here, and then I can divide by epsilon squared both in denominator and numerator. I get this. So you see that as epsilon goes to 0 and the limit epsilon goes to 0, this function epsilon by omega squared plus epsilon squared should become a delta function, because what is happening in this limit is that the function gets more and more peaked, because the width of the function is essentially epsilon, right? The width of the function is epsilon, and you see, but the integral minus infinity to infinity, this is conserved. So as epsilon goes to 0, the function becomes more and more peaked because the width of the function becomes smaller, but the integral of the function minus infinity to infinity, that's independent of epsilon, is simply equal to pi, right? And how the delta function is defined, the delta function is defined in this way, that d omega delta omega minus infinity to infinity is equal to identity. So essentially, this object in the limit epsilon goes to 0 should become proportional to a delta function, because all the weight of the function is only in this region epsilon, of order epsilon. So, but the integral is fixed. So basically, it should be proportional, and the integral is pi. So that is how you determine this proportionality constant pi. Okay. So one can also think of this object 1 plus I omega I epsilon as the principal value 1 over omega minus I pi delta omega. Okay, so now let us see its consistency with the Fourier transform. So as I said, that 1 over omega plus I epsilon, this can be written as dt minus infinity to infinity minus I e to the power I omega t times theta of t. Okay, and okay, and then I leave it to you to see the following thing, that you can also then this is simply exercise. You don't have to submit this, but do it at your home. So this is nothing but minus infinity to infinity dt e to the power I omega t theta of minus t. So that you can see that by doing the inverse Fourier transform first and show that theta minus t is equal to 1 over 2 pi d omega e to the power minus I omega t of minus 1 plus omega plus minus I epsilon. Try to do this, and there's an extra factor of minus because you have to close the contour in the contour in the because the contour will go clockwise whenever it will contribute, and then the inverse Fourier transform will be this essentially. Okay, so that's the way you can show it, and now you can see that if I add this to, what it means is that this object is, as I said, is minus I epsilon delta omega, sorry, minus I pi delta omega, and this object is minus then E1 over omega, and but then it's again minus I pi because the overall minus sign, and that makes it minus I pi delta omega, right? Because 1 over omega minus I epsilon would be principal value of 1 over omega plus I pi delta omega. So when I take a minus, overall minus sign, it will become like this. So this, now if I add this to, so this would be equal to dt, okay, so you're following, right? So what I've done is I've written this is equal to the principal value of 1 over omega minus I pi delta omega, and this object is, so principal value of 1 minus 1 minus I pi delta. So if I add this to, what should I get on the left hand side? I add this with this. If I add this to, on the left hand side, I get simply minus 2 pi I delta omega. On the right hand side, what I should get, I should simply add theta t with theta minus t, right? And theta t with theta minus t is what? What is the addition of these two? Can somebody tell me? What is theta t plus theta minus t?
A constant function, right?
Rectangular function. It's simply identity, right?
Yeah.
Because it's yeah. So now if you add this to, what you get is minus I minus infinity to infinity dt e to the power I omega t, right? Which means that 2 pi delta omega should be equal to simply minus infinity to infinity dt to the power I omega t, which is the basis of this inverse Fourier transform anyway, right? So this is how we get the inverse Fourier transform. So it means that the inverse Fourier transform of identity is delta omega. That's what it means, right? With an extra factor of 2 pi because of this asymmetric definition. Okay, so now we are equipped to see all this. So I hope all of this is clear, because this is something that is going to come again and again in many ways. So just to summarize is that these I epsilon factors are very important in physics, because whenever you see 1 over omega plus I epsilon, you should think in the Fourier transform way. In real time, it means that you're only taking contributions from time greater than 0. And whenever you see something like minus omega minus I epsilon, you know that it's the other way. It's so often this is called the retarded propagator, and often this is often called the advanced propagator, because, or acausal propagator. It propagates back in time. And yeah, so these are the things to keep in mind. And when you add the two, then obviously you get a delta function, because you take into account all possible. So a delta in omega means that you are simply doing a usual Fourier transform in time. Okay. Where you're taking contributions both from forward time and backward time, of course. And all right. So that is the main message of this exercises today. Let's go back to what we were doing before. So let me go back to the Lippmann-Schwinger equation now and show you that this is equivalent to the Dyson expansion. That is the goal of goal today. So now we go back to the expression that S beta alpha is delta beta minus alpha minus 2 I pi delta of E alpha minus E beta T beta alpha plus. So this was a definition of the S matrix, right? And let's start from here and see. So now we recall that the Lippmann-Schwinger equation told us that psi alpha plus is phi alpha plus d gamma t beta alpha. Sorry. No, it's okay. Let me then do it phi beta and E alpha minus E beta plus I epsilon. Remember, it's the plus I epsilon again. So using this, we can now derive an integral equation, or implies an integral equation for T beta alpha plus. So how to see that? We simply take the following thing on LHS and RHS of this above equation. We take this inner product by first multiplying with P, right? We apply this to this equation. And then we get, on the left-hand side, we simply get T beta alpha plus. On the right-hand side, we get, of course, V alpha beta, V beta alpha, and then we get plus D gamma, V beta gamma, and T gamma alpha plus, and then E alpha minus E gamma plus I epsilon. Okay, is this clear how I got this one? So to see this, what we have to do, I think I'm again goofed up here. 1 second, did I write it correctly? This should be d beta, of course. So first of all, I changed this beta to gamma, right? and this is what I did here. Is this integral equation clear, how I got this one? So what I've done is I have first of all changed beta to gamma here, right? Because okay, if you want, what I can do it already. Let me call it E gamma. Call this okay. And then what I do, I take this inner product on this side. So obviously phi beta V phi alpha is equal to V beta alpha. That's the definition of this matrix element. I use it here, I use it here, I get this integral equation for T beta. All right. So it means that if I try to rewrite T beta alpha plus in a series, what should I get is T beta alpha plus would be equal to V beta alpha plus D gamma V beta gamma V gamma alpha divided by E alpha minus E gamma plus I epsilon. Okay, so let me try to just simply and dot dot dot, and let's just see what this first two terms would imply. Okay. All right. So what we need to do is to rewrite this as a Dyson series. So here, it looks a little bit surprising because time doesn't appear here at all. Now, how we should introduce time? So let us first start with this expression, right? You have to go back to this expression and see what we get. So S beta alpha would be delta beta minus alpha, and the first series the first term that we get in T beta alpha plus is simply V beta alpha. Let us see what will happen. Then 2 pi I delta of E alpha minus E beta times V beta alpha. That is what we get here, right? That's the first term. And then there is order V square. The order V square term is simply this term. So now what we can do is simply use this expression that 2 pi delta E alpha minus E beta is equal to d tau. One second, just give me a moment. Okay, so coming back to what I was saying, then 2 pi delta E alpha minus E beta is minus I by, okay, there was, so I just use this formula again. So anyway, so this object is equal to d tau e to the power minus I by h bar E beta minus E alpha tau. Right, this is something I can use. Maybe I'm missing a factor of 1 over h bar somewhere. Yeah, I think there should be a 1 over h bar here. Okay, so that is what it is. So so I find this expression, or maybe, yeah, because it is delta, instead of delta omega, it is delta E alpha minus E beta. So delta omega is equal to delta E alpha minus E beta times h bar, right? So I'm simply using the fact that delta ax is equal to delta x by times a
mod of E.
Sorry,
With mod of E, modulus of it.
Modulus, yeah, that's right. But a, yeah, that is true. Exactly.
That is inside division.
Yeah. No, I was. Yeah, that is right. 1 second. Let me try to Yeah, it is by mod of A indeed. Yeah, of course, sorry. Yeah, and here omega is equal to E alpha minus E beta by H bar. So H bar comes on top. Okay, so if I use this here, I get that exactly. So I use this fact here. And then if I insert this in this expression, what I get is S beta alpha. Let me write it schematically, simply identity. I'm just writing this as an identity for the moment, plus it basically it means that it is delta beta minus alpha, nothing more. And then I get this term minus d tau, and there's a minus I here, and 2 pi is already included here, so I get minus I by H bar. So I take 1 over H bar from here, minus I from here, and I get minus I by H bar d tau e to the power minus I by H bar E beta. Actually, I could, so it doesn't matter. I can always change E here because delta, yeah, omega to minus omega will not change the answer. So I can also change it here because delta x is same as delta minus x. And similarly, the on the right hand side is the same. So I might have to choose a specific thing. Let me see. V beta alpha e to the power minus E alpha tau. So all of these are actually numbers. So I can simply move things around. These are not operators or matrices. So what is this object? Does remind you of? This is nothing but you see that if I write it this way, e to the power I H bar E beta tau, V beta alpha e to the power minus E alpha tau. It is the matrix element of phi beta, and then you have e to the power I H naught tau e to the V beta alpha e to the power minus I H naught tau phi alpha, right? This is a matrix element of this object. So essentially this thing is nothing but the matrix element of phi beta alpha H0, which is in the interaction picture. And then I have a tau. So what I can do, I see that S beta alpha is nothing but delta beta minus alpha minus I by H bar d tau minus infinity to infinity V beta alpha H0 tau. So I get the first term of the Dyson series from here, right? So basically what am I doing here? I'm just trying to convert an integral over energy to an integral over time, right? So I'm using, so this is what has happened, right? It looks like a little bit of abracadabra, but it's really straightforward maths here. And then I have an order V squared term. Have you followed up to here, what I've done?
Sir, can you explain the expression on top of this, the S beta alpha?
Okay. Look, what was this object phi V beta alpha by definition? By definition, this is simply the matrix element of maybe I should use the same kind of 1 second, simplified notation, phi beta V phi alpha, right?
Yes.
Now, what am I doing? I'm computing the matrix element of V in the H0 picture at tau. So what is V in the H0 picture?
No, not this expression,
Tau,
sir.
it is nothing but, wait. Okay, and now if I compute this beta alpha element, I get this object, right, which I wrote here. So this is why I said this is equal to nothing but V beta alpha H0 tau. So, but you are not asking about this, sorry. What you were asking about? Sorry, Akshay.
Sir, I was asking this expression, S beta alpha equals to delta of S beta minus alpha minus iota batch, but here this expression where you term the use expression exponential I H, but E beta tau V beta.
Well, you see, or here what I've done, I simply replaced this thing, right? I simply replaced 2 pi I delta this object by the integral.
Okay. But sir, then how then we use that?
Well, v beta alpha can be actually taken out of the integral because it has no time dependence, right? So this is what I simply replace this by the integral.
But sir, in the expression here, you have used the h naught, where we use the e beta, e of beta.
Yeah. So h naught is an operator where this is a number, but I'm saying it's a matrix element of this object. That's what I explained.
Okay.
It's a matrix element of v alpha beta, v beta alpha in the H0 picture.
Okay.
In the interaction picture. That is where the evolution with respect to H0.
Okay, very good.
So this is a matrix element of this object, this operator. So that's why I didn't put this thing. So that's why I'm taking time here again to explain this, that if this is so, then v beta alpha H0 tau is nothing but equal to the matrix element of this object, phi beta e to the power I h naught tau, v hat e to the power minus I h naught tau, phi alpha, right? And this object is nothing but e to the power I by h bar. I always sometimes forgot to write this bars. E beta tau, v beta alpha e to the power minus e alpha by h bar tau. So this is a matrix element. And what I'm integrating here is this matrix element, right? Does that answer the question?
Yes, sir.
Yeah. But if you think of S as an operator, then you could write it this way. S as an operator is identity, right? Because again, S as an operator is a matrix element. You can think in terms of phi beta, phi alpha. This is a complete basis of states. So I can always take a matrix element with respect to any complete basis of states. I take with respect to this phi alpha. And this is then as an operator, this identity minus I by h bar, minus infinity to infinity d tau, time. Okay, there's only one operator here. I can write it more simply. Now this operator has the same matrix elements. This reproduces the matrix elements of S, right? So S as an operator has to be this. Is it clear?
Yes, sir.
Okay. So now let us look at the second term. The second term, what it should be is simply this, and let us see how to, right? The second term, let us look at the second term. Again, the second term is minus 2 pi I, because this object is always there. This multiplies the whole thing. And then you have d gamma, v beta gamma, v gamma alpha divided by e alpha minus e gamma plus I epsilon. Okay. So now let us try to see how to rewrite this. So first, I will write both this and this object as functions of time, right? So I've used that. So I know how to write. If I think this as omega prime and this has some omega, I can then do this too. I do the Fourier transform of them. So let me write it down. It should be obvious. So you see that this is nothing but reproduces this factor 2 pi delta omega, right? This is minus infinity to infinity. This reproduces 2 pi delta of e beta minus e alpha times h bar, and this is divided by h bar. So this is what it reproduces. And now I have to reproduce this object. And I know how to do it. It is minus infinity to infinity. And so there's a d gamma and d tau tilde. I have to use a different tau. And then e to the power I by h bar, e alpha minus e gamma tau tilde. And then I have v beta gamma, v gamma alpha. Okay, is this clear? Because this object is nothing but, I'm sorry, I forgot to write an important thing. sorry, there is a theta tau tilde, and then V beta gamma, V gamma alpha. So basically this factor, E alpha minus E gamma plus I epsilon, can be simply obtained by integrating the Fourier transform of theta. The Fourier transform of theta would give me this denominator, 1 over E alpha minus E gamma plus I epsilon, okay? So now let us do a change in variables or try to see how it works out. So if I rewrite this, you see the integrand is essentially has this E beta here. So this I can write as e to the power I h bar E beta tau. And what is the prefactor of E gamma? E gamma is only here. So this is e to the power minus I by h bar E gamma tau tilde. And E alpha appears twice here and here. And this factor is to the power minus I h bar E alpha tau minus tau tilde. Okay, wait a second, I have to charge this iPad. Yeah. Okay, so right, I just collected terms below here, or all the tau dependent factors here. And now you see if I collect it like this, it's obvious what to do. Tau should be renamed as tau1. Tau tilde should be renamed as tau1 minus tau2, which and if we will see why. And then this factor tau minus tau tilde, right? So tau minus tau tilde will be tau1 minus tau1 minus tau2, and this is nothing but tau2 itself, right? So I simply do this change of variables. And if I write in terms of tau1 and tau2, what happens is as follows. This expression above becomes so theta tau tilde will become tau tilde is tau1 minus tau2. So this expression is then minus I square by h bar square d gamma, and then d tau1, d tau2, all of these going from minus infinity to infinity. And then there is a theta of tau1 minus tau2. Theta tau1 minus tau2 comes from the tau tilde is tau1 minus tau2. And I had a theta tau tilde here originally. And then I have to write this prefactors. Now, so here is only tau, and tau is tau1. So e to the power minus I by h is e to the power I by h bar E beta tau1. Okay. And then I get e to the power minus I by h bar E gamma. And E gamma tau tilde is tau1 minus tau2. So I write tau1 minus tau2. I just simply rewrite this here. And then tau minus tau tilde is tau2. So I get e to the power minus I by h bar E alpha tau2. And then I have V beta gamma, V gamma alpha. Now, what does this remind you of? So you see, this is nothing but, so let me rewrite this in this way. Again, minus I by square by h bar square d gamma minus infinity to infinity d tau1 minus infinity to infinity d tau2 theta of tau1 minus tau2. Now this theta of tau1 minus tau2 means that the tau2 integral actually doesn't go all the way up to tau infinity. It goes all the way only up to tau1. So I can remove this theta factor and instead put this upper end of the integral as tau1. Okay, that's what I'm going to do. And now you see that this I can rewrite in this way. I can rearrange the factors that. So let me write in this way: V gamma alpha, and I write e to the power minus I by h bar E alpha tau2. And there's a gamma here. I squeeze this factor here because these are numbers. I can squeeze these factors anywhere I want. E gamma tau1 minus tau2, right? And then here I write V beta gamma, and then I write this factor at the end, e to the power I by h bar V beta tau2, sorry, tau1. Okay. Now, what do you see here? Now, what is this object, right? And so you see that this object is nothing but, so first I write V80 tau 2, and okay, so let me write also the matrix element. So this V gamma alpha, so this object is nothing but V gamma alpha 80, the tau 2, right? This is a matrix element of this object. If I just write, if I further divide this, e to the power e gamma tau 1, e to the power I by h bar e gamma tau 2. If I take this object together, this is nothing but this. Now this object is nothing but V beta gamma h0 tau 1. This object is this, and this object is this, right? And then you see that I have I also have this d gamma integral, but this d gamma integral is nothing but inserting a complete set of states, and so this is nothing but minus I squared by h bar square d tau 1 d tau 2. The tau 2 integral goes from minus infinity to tau 2. This goes from minus infinity to tau infinity, sorry. And sorry, this goes up to tau 1. And then this object is nothing but the matrix element of the following V80 tau 1, V hat 80 tau 2, and the matrix element beta alpha of this operator. Then finally, you note that we can do the same trick that if you introduce time ordering, then we get two such yeah, let me finish here, sorry. So if I introduce, so here tau 1 is greater than tau 2. That's how it is always ordered in this expression. And now if I because of this theta function, it gets now if I introduce the time ordering, then I get two contributions, and I can rewrite this as minus I square by h bar square 2 minus infinity to infinity d tau 1 d tau 2, again minus infinity to infinity, but then I introduce a time ordering, which is v hat 80 tau 1 v hat 80 tau 2. Yeah, let me please ask. Yeah, Akshay, you are asking or somebody else?
Sir, where does the integral over gamma d of gamma integral in the above expression?
Yeah, the d gamma integral, look, that's what I'm said, that you see you get it here v beta gamma and v gamma alpha, and you have inserted and you're integrating over d gamma, right? So you have inserted a complete set of states, and look, you have, if you take an operator A, operator B, right? And you take its alpha beta matrix element, that's equivalent to taking A alpha gamma, integrating over gamma, because you're inserting a complete set of states. You are simply using d gamma, phi gamma is equal to identity, and then b gamma beta, right? Akshay?
Yes, sir, I got it.
Okay, got it, good. Okay, so you see that the second term, so then what we see that the S matrix, and okay, so I should have written here beta alpha. But then if I think of the S matrix as an operator, I can remove, what we so see is that if S is an operator, the first term gives this, the second term gives you, sorry. The second term simply gives you minus I squared by h bar square 2 d tau 1 d tau 2 minus infinity infinity minus infinity infinity, and the time order product of v80 tau 1 V80 tau 2, right? So I give it as exercise. This is the exercise that you should submit next semester. Sorry, the exercise that you should submit in the next week, because it's, I think, not a hard, or you can try at least to submit as soon as possible. So exercise is to show that if I do this recursively, use an inductive proof, and if you take all of these terms that I'm getting from this integral, so if I take this T beta alpha and I write the integral series for T beta alpha, I will keep on getting all kinds of terms of this kind, right? So if I write this integral equation for T beta alpha, I wrote the first and the second term, I would get all possible such terms one by one, right? And what I ask you to do is a inductive proof. I've already showed you for the first two elements how it works. And if I keep going on like this, you will see that I will be able to prove that the S matrix as an operator is simply identity plus some n is equal to 1 to infinity minus I to the power n by h bar to the power n by factorial n d tau 1 d tau n, and then the time order product of V80 tau 1 to V80 tau n, right? And this is something that we already showed is nothing but U tilde U dagger, right? So this is the S matrix as an operator. So what you see is something remarkable, that you can rewrite everything as in time rather than as this time independent way. And this gives you a much better understanding of what is going on, okay? So any question up to here? I think it's actually 2-3 line proof. If you really think about it, it's a simple inductive proof. Just think about it. You don't have to really work hard to do this proof. So it should take you only 1 hour of your life to do this assignment, and you can submit it next week, okay? Please do that. Okay. Now this is a very fundamentally beautiful observation, because you remember in what we did in quantum mechanics, when we wrote this interaction terms V hat, we wrote it as sum over A, some coefficients, which could depend on time, of course. But for the moment, I say that, okay, we can put some time dependence to be general. Okay, here when we are doing these things, we assume that V is time independent, but everything goes through. If we, in this way of doing things, in the time, in an explicit time dependent way of doing things, everything goes through, even if it is time dependent. So now, and then we had a series of operators like O hat, A. In quantum field theory, A basically would stand for the positions X of space. So basically, instead of a summation, you have an integral. So V hat in quantum field theory would be simply d cube X, Ga X T, and O hat X. Of course, there can be other indices too, which are simply, but maybe what I can do, I can rewrite this as sometimes what people do.
It's not D4X, is it? Or it's only over space.
It's only over space, yeah. So of course, yeah. What do you mean it is D4X? Why do you expect it to be D4X? I mean, this is an operator in some picture. No, it's certainly not. I mean, it is only a function of X, right? So this is an operator, and A is the label here, which becomes X. Okay. All right.
So, but label at each point is a space-time event, right? So.
No. Wait a second. Look, again, go back to quantum mechanics. In quantum mechanics, these operators don't have time levels, right? That is how we define it. Yeah, eventually it will become time dependent. If I put just hold on. I'm coming to that. So now what you could do is, so what people usually do when they write H interaction X e to the power minus H0 t, let me put it this way, e to the power I H0 tau or t H. So here is simply the interacting part of the Hamiltonian. So what you assume is that all the interactions are local. That is, it can be. So this is again a very crucial assumption that all your interactions are local. If the interactions are not local, then you do not have the cluster decomposition principle, which I said that you don't have like an experiment here, an experiment in Andromeda galaxy would be independent of each other. That will not happen. So it's very important to assume that the interactions are local. So then you get this expression that H interaction X so then this becomes time dependent, and you can think of it this way: H interaction xt, where interaction here doesn't stand for, or even can stand for two things. One is the actual, it just captures the interacting part of the Hamiltonian density, and it also can stand for the fact that it's an interaction picture because you are evolving in H0 here. So this is often what people define as simply H interaction xt, or they even call it H hat interaction X, where X stands for now this 4-dimensional point X and T. So now what you could do, you can rewrite the Dyson series in a nice way. The Dyson series basically becomes S hat is sum over n is equal to 0 to infinity. I also put the identity here, minus I to the power n by H bar to the power n. And now you see that for each of these V's, I should get an integration over X and also integration over time, right? So which I can club together and now say the integration is over all 4-dimensional space, d4x1, d4x2, d4xn, over all space and all time, and the time ordered product of H interaction x1 to H interaction xn is a factorial n, of course. All right. So this is the expression that we ultimately will deal in quantum field theory. So it will be an interaction. It would be simply a time ordered product of this local operators, and we integrate over all space and all time. Now, the interesting thing about this expression is very it's simple, that if you take the time order, that the time ordering is invariant under Lorentz transformations. Okay, the time and ordering is invariant. So if T1 is greater than T2, then it will, so basically theta of T is Lorentz invariant. So if you take any Lorentz transformation, any boost, a boost is not going to change the causal, because the time ordering is invariant under. It's not going to change the causal structure. So basically, this time ordering remains the same under this things. Sorry, what I said is total nonsense. Sorry. Let me. I'm really sorry for this. Sorry. Wait a second. Okay. 1 second. What I said is not correct. Wait. What I meant to say is as follows: that no, what I said is total nonsense. So the time, sorry. What I should have said is something different. So the time ordering is not Lorentz invariant, of course. If a time ordering within the light cone is time ordering within light cone is Lorentz invariant. That's what I meant. So what I mean to say is as follows. So if you take this light cone, and outside the light cone, of course, if you take two events, this and this, you can look, you can have a, so you can have, so this is this is time, this is space. Or sorry, this is time. Let me call this is time and this is space. Sorry, this is time, this is space, and this is some t is equal to 0 in one frame, and so this is say t is equal to 0 in another frame. So this is t prime is equal to 0. If you look here, then these two events are simultaneous, whereas in this frame, in the new frame, this event has occurred before that, right? So time ordering outside the light cone is not Lorentz invariant, right? Whereas time ordering within the light cone is Lorentz invariant. However, so now you see that this expression, in this expression, we are integrating over all space and time. So this expression S hat is Lorentz invariant provided okay. So provided, so this time ordering means a specific ordering. If they're within the light cone, it is independent of the frame, right? This time ordering, maybe I should change my color. So this time ordering, if they're within the light, outside of the light cone, sorry, if they're inside the light cone is invariant from one frame to another. However, outside of the light cone here, it will depend from one frame to another. However, the ordering doesn't matter because the operators commute outside the light cone. Okay. If its two operators are not within the light cone, then any kind of ordering will come. So it implies that if I put these two things together, that this comes from causality. So if I put locality and causality of the interactions together, and locality means that all of these, locality means simply means a statement that this V can be written as some kind of local operators, as some kind as an integration of a local operator. So this is the locality that I'm putting in, and then I'm putting causality, which implies that there is that the two operators outside the light cone commute. If I put in this locality and causality together, so locality plus causality implies S matrix S is Lorentz invariant. If H X is a Lorentz invariant scalar, because if it's a Lorentz invariant scalar, then these integrals are Lorentz invariant, right? If I integrate d4x phi x and phi of x is a Lorentz invariant scalar, then this integral is Lorentz invariant. So essentially, it means that the S matrix has a good yeah, the fundamental processes of the universe would be, or of the theory would be independent of which Lorentz frame we are using to define them, provided these two are true. Now, you have to also important that this that we should also have that this is also causal and local together. And the other thing that is something that we will see that we also get, especially this cluster decomposition, which I was just vaguely, okay, so this is something that I'm going to tell you now, this cluster decomposition property.
So the locality
that should follow from. Yeah, tell me.
So the locality is in space or it is in space time?
It's sufficient, it's in space, right? Because yeah, okay, it's also in time. You're right. I mean, you see that, yeah, it's a locality in both space and time, because as I said that, you remember I made a similar, even before here, I made a similar thing that V hat is not of this form as dt1 minus infinity to some 0, or minus infinity to some 0 dt2 and some ft1 minus t2 into some kind of operator, or maybe some. Yeah, I can also, so this is both in space and time. I'm not assuming, so this operator is local in time, right? But that is something that we already assumed in the case of quantum mechanics, right? This is something, the locality was already in time was assumed before. But here, the more important thing that the new thing that we brought in is also locality in space, right? So suppose a non-local operator could be of this form. Let's write an example. Suppose v hat was equal to d cube x, or d cube x and d cube y, some g x minus y t and h interaction y, something of this kind, for example. So that would have been a very non-local expression. It's not a, so this is non-local. It simply means that you could, there's only one integration over x, and the operator, you are simply integrating an operator at every point in x with a local weight. And this is what is often called the coupling constant. And this coupling constant, you can in principle also make it a function of time and space if you want, or you could simply, so of course, if it's a fundamental theory, it is what it is, simply a constant. But if you are engineering some field theory on a lattice or in a cold atomic trap, then you can engineer the coupling constants also to depend on space and time. So this is what it is. And these coupling constants are scalars, and this is also a scalar operator. I'll give a more precise definition of what you mean by scalar operator. But for the moment, you should just think of it as the matrix elements are scalars or something of that kind. We will try to be more precise later. So for the moment, it's sort of a heuristic kind of a picture that if I put in locality and causality together, then it should be clear from the expression that this S has a right, or S commutes with Lorentz transformations, that S is consistent with Lorentz invariance of the theory. Okay. But it's important to have both locality and space and time. That sort of is obvious from this expression also. So now let us see how it leads to this cluster decomposition property in the last 10 minutes I have. So is it clear for the moment that that why locality and causality are both important? If not, let me know. Please ask me again. Okay. So if not, like, let me then move. Bolo.
Like now H is an operator and not like a function of X, right? So Lorentz invariance still, like when we multiply with that matrix gamma, like gamma transpose, like that's how we, I mean, how do you define like action of?
So what we will see, yeah. So what we will see that, well, I will eventually do that. Okay. What we'll later see is that we will have one class to this when we go to the explicit construction of field theories. So let me maybe already say it a little bit now. So for every Lorentz transformation, lambda should be represented as some u lambda, right? In the so there should be an operator, because you see that any physical transformation should be a unitary operator in quantum mechanics. So corresponding to a boost lambda, right, which acts say on positions or something, there has to be an operator u lambda, unitary transformation. And therefore you take any you take any kind of field operator, right? Its transformation under lambda would be simply u dagger lambda phi hat xt u lambda, right? And this will be exactly equal to phi hat prime lambda. I can write all of these things together as X. So this is exactly what I mean by Lorentz invariance of the operator.
Okay, okay.
Yeah, so but this will be already in the, so we'll try to see the simplest operator algebra that reproduces this transformation, and voila, we will get the Klein-Gordon equation. That I will simply see that we'll create, so what we will later do is that it will take only like 30-40 minutes for me to do that. It's a very elegant construction. I just put locality, causality, and Lorentz invariance, and then you see that the simplest field theory is nothing but the Klein-Gordon equation, the Klein-Gordon field theory. And I'm not using, I will not use to, I will not be starting from a Lagrangian and quantizing the theory. I will simply get it from these principles. And later we will see that in the classical limit we get, so okay, so this the field equation for this operator, the operator will satisfy some equations. And if I take the h bar goes to 0 limit, then it becomes a classical equation. And this classical equation is reproduced from a Lagrangian and things like that, which is the Klein-Gordon Lagrangian. So we will take this route, and so I will become more precise about what you mean by Lorentz transformations and what are these operators explicitly. So I will construct these operators by how they act on states, or I just give appropriate definitions of these operators, and we will move on from there. Okay, so just hold. So so all of this is going to become very easy later. But actually, we are now looking. We are actually covering the harder parts of the subject, not the easier parts of the subject. So if you have sailed through, you know, the 3 more lectures, then you know all the tough work is almost done for you, because these are the harder parts of the subject to understand. This operator algebras, how they work. Okay. Okay, so now let me, in whatever time I have left, approximately 6 minutes, let me try to tell you about the cluster decomposition principle and how it works. So think about in this way that you have these alphas can be thought of as some kind of momenta of the incoming particles, P1, P2, Pn, and betas are the in states, and this was the out state. You have P1 prime to Pm prime. Okay, so these are your in state and out state. And suppose you are in a universe with a process. So here you are here on Earth, and here there is something on planet X in Andromeda galaxy. Okay, and if you think about in state, right, it will be very entangled with this alpha state. Here there's very entangled, right? P1, P2, Pn are very entangled. And the beta state is also very entangled. So there is a lot of quantum entanglement in the state. If it is suppose a pure state or something of that kind, it could be very entangled. So in principle, of course, it's not completely pure state and entanglement is minimal and things like that, but that's a separate issue altogether. The point is that suppose you're looking at some kind of experiments of this kind where, so P1, P2, P3 goes to say P1 prime, P2 prime, P3 prime, P3, P4 prime. So what I mean to say is as follows, that P1 plus P2 plus P3 should be equal to P1 prime plus P2 prime plus P3 prime plus P4 prime. So there's a subset here and a subset there where momentum is conserved. And also you have EP1 plus EP2 plus EP3 of these particles. The energy of these particles is essentially square root of P1 square plus M1 square and so on and so forth is equal to EP1 prime plus EP2 prime plus EP3 prime plus EP4 prime, right? So what is happening is that you are looking at processes where you have energy momentum conservation. So there could be other particles somewhere else but these two processes are sort of occurring such that the energy momentum vectors, so energy and momentum are conserved in two subsets. Okay. So, right. So if that is the case, and so what we are going to show is as follows. So if you take this S matrix and I define some kind of Fourier transform of the S matrix in the following way, that I take simply the okay, so this is a matrix element. This was my in state, which I called collectively alpha. This was my beta state, and do a Fourier transform of that, e to the power I okay. So I'm doing a Fourier transform of this matrix element. So this should be obvious. What am I doing? I'm just taking this momenta P1 and this final momenta Pm prime, and this is basically, then it becomes a space transition amplitude, right? It happens like this transition is occurring at specific spatial points, right? So this is what I call this kind of a Fourier transform of this. So what it will happen is that this matrix element will factorize into two parts. A part that involves only this transformation that I'm looking at here, and that will be the other subset of transformations that is where the energy momentum is conserved independently. So I will try to give so in tomorrow I will try to give a proof of this theorem. Okay, a proof of this cluster decomposition. So let me try to write down explicitly. So this would then factorize into S. So this is cluster 1, and this is cluster 2. So it will simply have this cluster 1 and cluster 2, where the cluster 1 will involve those momentums which are conserved on their own, and the other set would be that momentum and energy that is conserved on their own. Okay, so I will try to give you a very simple and very simple proof of this. So, and try to explain why it leads to this factorization, this cluster decomposition property. I think this is a very important statement that needs to be understood. And you will see that when you actually do the Feynman diagrams, it automatically reproduces this cluster decomposition property in a very easy way. So yeah. So maybe I should stop now, because I can simply continue next time rather than take more time now. Because it will, if I say something more, it will not be very clear. So let me then stop today's class. Any question? Yeah.
Yeah. So like, I still don't understand the motivation for us to do this S matrix formalism, and why is it more fundamental than like any other approach you could have taken? Like this looks like an experimental quantity, S beta alpha, as you said, but why is it so fundamental in our theory? Like,
Okay, so there are many ways to answer the question. One way to answer this is, suppose you are looking at any arbitrary material or any arbitrary medium, what is happening, or in the sun, for example. Essentially, effectively, any process can be thought of as made of this independent small S matrices, like a product of this S matrices. Why? Because if the interaction time, as I showed you this explanation, when you take this d beta integral of the evolution, if you look at time much greater than the interaction time, right, then essentially your and the width of the wave packets, then essentially you can think of it as an S matrix process, right? Where, because time effectively is in infinity. So what we showed, remember, it was mod t greater than equal to h bar by delta E, and interaction time, where interaction time is defined by the poles of this T beta alpha plus, remember? So basically it's effectively a S matrix process. Now what happens in a gas? In a gas, what is going to happen if you have weakly interacting particles? Each particle has a definite momentum and a definite momentum, right? And then when the wave packets overlap, there is some kind of S matrix process, and then it transforms into something else. So all kinds of processes that are going to happen in, say, a gas is effectively different independent S matrix processes, right? So you should be able to understand any material, or fundamentally any process which is composed of weakly interacting particles or something in this language. Now, obviously, is going to if what is going to happen is that if you make the medium very dense, then all the wave packets are going to overlap always, and then you do not have any freely propagating particles at all, right? So then you have to do something else. Then you have to, but then what is going to happen is that you have to redefine your system. So okay, so that is what is going to happen, is that you can always, in that case, you can always still think of the medium in most cases as weakly interacting quasi-particles. So you have different kind of particles which are not the original particles, but something else. And so then, for example, what happens for electrons in a metal, the masses get renormalized because of the wave packets overlap very strongly. But then still you are able to describe the full system now in terms of these weakly interacting stuff, and you can use this normal S matrix methods. So, but the properties of the electron in a medium would may be different from the properties of electron outside of the medium. But then there are some new kind of systems where people have found where there is no quasi-particle description at all, and then everything is like this is going to fail, right? All of these methods are going to fail, and this is something, of course, at the forefront of research today, where media that we cannot understand in terms of quasi-particles. But as long as we can understand any medium in terms of quasi-particles, and we should be able to construct an S matrix way of understanding any process. So any big process is basically product over different independent S matrix processes. Okay. All right. So let me then stop this lecture and we see each other again on Tuesday.
Thank you.